You know, when you're looking at the window of a plane and you just kind of marvel at how this massive, heavy machine is just flying? Well, the magic behind that is a force called lift. But here's the wild part. The very force that holds the plane up in the sky also creates another force that's actively trying to hold it back. It's this crazy paradox, and today we're going to pull back the curtain on it. So, what is this invisible price, this invisible hand that every single aircraft has to fight against just for the privilege of staying airborne?
Well, it's called induced drag. And no, this isn't like the regular wind resistance you feel when you stick your hand out of a car window. This is something else entirely. It's an unavoidable, baked-in consequence of creating lift. You literally can't have one without the other.
Okay, a really simple way to wrap your head around this is to think of it as the cost of doing business for a wing. You want lift, you gotta pay the price. And that price is induced drag. But to really get it, we need to look at what the air itself is doing right at the tips of the wings. And that brings us to the real troublemakers here, wingtip vortices. These swirling, angry spirals of air are the direct cause of induced drag. Honestly, if you understand how these things are born, you've pretty much understood the whole concept. So check this out. It all boils down to some super basic physics. High pressure always wants to move toward low pressure. An airplane wing works by creating high pressure underneath it and low pressure on top. Now, that high pressure air below is just desperate to get to the low pressure party on top. And the easiest escape route? It just spills right around the edge of the wingtip. When that happens, it creates this powerful, swirling vortex, kind of like a mini horizontal tornado trailing behind the plane. Now, this vortex isn't just some harmless little swirl. Oh no. It's a powerful force that actually yanks the air downwards as it comes off the wing. We call this downwash. And this downwash messes everything up, changing the direction of the air that the wing is flying through. So because the air is now flowing slightly downwards, the wing has to tilt up a little bit more just to get the same amount of upward lift. But when it does that, the entire force of lift gets tilted slightly backward. And that tiny rearward component of the lift force, that is induced drag. See, it's not a totally separate force. It's just a piece of the lift vector pointing in the wrong direction, all because of those vortices. Okay, so we know what it is and where it comes from. The next logical question is, how do you deal with it? Well, pilots and aerospace engineers basically have three main levers they can pull: the aircraft's speed, its weight, and of course, the shape of its wings. Let's break each of these down, because they have a huge and sometimes a really counterintuitive effect on just how much drag a plane has to fight. All right, first up is weight. This one's pretty easy to grasp. The heavier the plane, the more lift it needs to stay in the air. To get more lift, you have to create a bigger pressure difference between the top and bottom of the wing. And a bigger pressure difference means, you guessed it, a stronger, nastier wingtip vortex. More vortex, more induced drag. Simple, right? Okay, pop quiz time. If a plane doubles its speed, does its induced drag go up or down? I mean, your gut probably tells you it goes up, right? More speed, more of everything, more drag. But the real answer is actually the complete opposite. So here's the logic. When a plane flies faster, way more air is rushing over the wings every second. This means the wings don't have to work nearly as hard to generate the same amount of lift. They can fly at a much lower angle of attack. A lower angle of attack means a smaller pressure difference, and that means much, much weaker vortices. Weaker vortices, less induced drag. It all clicks together. And the effect isn't small, it's huge. Because of the way the physics works out, if you double the speed, you actually cut the induced drag down to just 1/4 of what it was before. It's this wild inverse relationship that's absolutely fundamental to flying efficiently. And that brings us to our third lever, the shape of the wing itself. Engineers call this aspect ratio. Don't let the term scare you. It's just a fancy way of describing if a wing is long and skinny, like on a glider, or short and stubby, like on a fighter jet. And this is just a perfect example of a classic engineering trade-off. A long, thin, high aspect ratio wing is incredibly efficient. Why? Because the wingtip, where all the bad stuff happens, is a much smaller proportion of the total wing, so you get way less induced drag. But a fighter jet needs to be incredibly agile. It needs to roll on a dime. That requires short, stubby wings, and the price they pay for that amazing maneuverability is a ton of induced drag. So you might be thinking, why don't we just put long glider-like wings on every plane? Well, those super long wings are also super heavy. They create enormous bending stress where they connect to the fuselage. They're sluggish and slow to respond. And yeah, you also have to worry about the wingtips scraping the runway during a crosswind landing. It's always, always a compromise.
This is where things get really cool. Since you can't just make wings infinitely long, engineers have cooked up some absolutely brilliant ways to cheat the vortices and trick the air into behaving itself. I mean, they've tried all sorts of stuff over the years. They've put flat plates on the wingtips, used the fuel tanks themselves as barriers, and even just drooped or raised the wingtips. The goal's always the same: do something, anything, to make it harder for that high-pressure air to spill over the top. But by far the most successful, the most common solution, the one you've definitely seen a million times at the airport, is the winglet, that sharp-looking, upward curved bit at the very end of the wing. But wait, it gets even cooler. This is the mind-blowing part. A really well-designed winglet doesn't just block the airflow. It's actually a tiny little wing in itself, and it's perfectly angled to interact with that swirling vortex in such a way that it actually generates a small amount of forward thrust. That's right, it creates negative drag. So a winglet is doing two amazing things at once. First, it's a physical barrier that weakens the vortex. And second, it cleverly harnesses the energy that's already in that vortex and uses it to give the plane a tiny little push forward. It is just an incredibly elegant piece of engineering. So let's put it all together. The big thing to remember is that induced drag is a low-speed problem. It's at its absolute worst during takeoff and landing, when the plane is slow and the wings are working their hardest to create lift. Once you get up to cruising speed, another type of drag, called parasite drag, takes over as the bigger enemy. The whole game of efficient flight is managing the trade-off between these two. And that really is the key takeaway here. Induced drag is that inescapable price you pay for lift. It's a low-speed menace, for sure, but through a deep understanding of aerodynamics and some really, really clever engineering, we've found ways to fight back and minimize its impact.
The story of induced drag is just a great reminder that in engineering, and maybe in life, there's really no such thing as a free lunch. Every solution creates a new set of trade-offs. And that makes you think, doesn't it? What are the induced drags in the other amazing technologies we rely on every single day? What are the hidden costs of our smartphones, our electric cars, our AI? Something to chew on. Thanks for tuning in.